Welcome. It's about that time again for another physics exam. So let's review the key questions from Chapter 4, or at least the questions I looked at when making the exam for Chapter 4. Number 20. Assume that an object has negative acceleration. That's just a statement. So, okay, acceleration is negative for right now. A. Is it possible that its speed can be increasing? If so, how? One thing we've spent a lot of time talking about in Chapter 4 is how acceleration is one of those words that its actual meaning, its actual definition is a little bit different from how people tend to use it in day-to-day speech. In day-to-day speech, when people say accelerate, they always mean speed up. We've discussed how that's not always the case. Slowing down is also acceleration. Turning, changing direction is also acceleration. So there's a lot of different situations in which acceleration can be positive, can be negative, could be speeding up, could be slowing down. For here, is it possible that its speed can be increasing? Certainly, as long as we're trying to travel into the negative direction. So for example, let's say I've got a car. I apologize, I am not an artist. So here's my car, maybe a strange bus. It's going in the negative direction. We'll say left is negative here. So my velocity is negative. If I'm traveling in the negative direction and I have a negative acceleration, that would cause me to speed up. If I wanted to prove that with an equation, here's how we calculate final velocity. Let's say that our initial velocity was negative 5 meters per second. We've got a negative acceleration of, we'll keep it simple, we'll say negative 1. And we're going to accelerate for 5 seconds. Negative 5 plus negative 1 times 5 would be really just negative 5 minus 5, so negative 10. We got faster in the negative direction. So yes, in the negative. That would answer the question for us. B. What must the signs of velocity and acceleration be to ensure that speed is increasing? Well, if we just look at part A, we had negative velocity and we had negative acceleration. As long as they're both negative, we're speeding up. The flip side of that would also be true. If we were traveling in the positive direction, if V was positive, we would speed up if the acceleration was also positive. So to answer the question, as long as your velocity and acceleration are the same sign, both positive, both negative, then you will be speeding up. It's only when they have a disagreement, one's positive, one's negative, they kind of butt heads, and that causes things to slow down. The rest of the questions we'll look at are a little bit more math focused. So here, we've got a car traveling 15 meters per second. I'm going to go ahead and list my givens. Especially if I'm taking an exam, I have plenty of time because I know the teacher that made the exam knows roughly how long it's going to take and planned for you to have time. So list your givens, don't be in a rush. Car is traveling at 15 meters per second, meaning it was already going that fast. So that'll be my initial velocity. It goes down a hill where it accelerates at 3 meters per second squared. Acceleration, 3 meters per second squared, for 4 seconds. It's going to be accelerating for 4 seconds. So that's my time. And then how fast is it going at the end, at the bottom of the hill? We're looking for final velocity. So we've got acceleration, time, and 2 different velocities. Luckily, we have an equation that has those 4 things and only those 4 things. That being the mathematical definition of acceleration. So we could start there. I'm trying to get VF by itself. So I'll multiply time up, or multiply both sides by time. That'll give me acceleration times time is equal to the change in our velocity. I still want to get VF by itself, so now we'll add the initial velocity. over to the left side. So all in all, AT plus VI is equal to VF. That's how that comes out. Or more frequently, you'll see me write this equation as VF is VI plus AT. I just like how this format looks a little bit better, but these are the same equation. It's just rearranged. I put VF on the left because I like to have my singular variable on the left, and then I flipped AT and the VI around. But with addition, we can flip-flop them back and forth without messing anything up. But now we've got an equation that can work, so we can plug in our values. VI is 15, acceleration is 3, and our time of 4. So that's 15 plus 12 for a grand total of 27 meters per second. Going pretty quick. Moving right along. Next up, number 30. Very, very similar question, so I'll go through this one a little faster. There's my givens. My letters kind of ran together, but it still kind of looks like it says givens. A car is traveling at 15 meters per second. We've got the initial velocity. It was already going that fast. And it's going to accelerate for 5 seconds. That's a time. Its acceleration is 2 meters per second squared. And we want to know final velocity. Well, we figured out an equation for that just a moment ago. That being VF is VI plus AT. Plug in our values. 2 for our acceleration, 5 for our time. So we've got 15 plus 10 for a grand total of 25 meters per second. Almost the same. Not quite as fast. So if I was going to prep for this exam, this is one equation I would definitely have on my note card. It's a very common one that we end up using because there's a lot of situations where we need to calculate something's final velocity, and that'll be true going forward well into Chapter 5, Chapter 6, and even Chapter 7. Next up, 32. Rachel is walking at 3 meters per second when she walks into a glass door and stops in 0.05 seconds. What's her acceleration? Starting with the givens, always a good place to start. So she was already walking at 3 meters per second. That's her initial velocity. Then it says she walks into a glass door and stops. So her final velocity is going to be 0. She stopped in a really short amount of time. There's our time. And we're looking for acceleration. So we're actually going to be using the same equation from before, but we can actually leave it in the form it started in, as in the mathematical definition of acceleration, change in velocity over change in time. We don't need to do any fancy algebra. We can just plug in and solve. VF was 0, VI was 3, and our time of 0.05. I will have to grab a calculator for that one though, so give me just a moment to plug that in. That'll be negative 60 meters per second squared. Now for those units, if you know you're looking for acceleration, then already you should know the acceleration units are meters per second squared. We've been using them well enough already, but if you're ever in a situation like you're taking a test and for whatever reason you just cannot remember what the units are for acceleration, there's a trick to it. You can just look at the equation. On the top, we've got velocity, so that's meters per second, and on the bottom we have time, which time is just measured in seconds. So we have meters per second, or we could write that as meters per second multiplied by 1 over seconds. And then just multiply across the top, we get meters on top, seconds times seconds on bottom, or we could write that as seconds squared. But most of us probably will just remember meters per second squared is for acceleration because we've been saying it so much. But we can analyze the units, and we will do more of that unit analysis in the future. But moving right along to number 36. Jane is riding her bicycle at 10 meters per second. So here she's already traveling at 10 meters per second. That's her initial velocity. When she begins to decelerate at 1.5 meters per second squared. Now we got this dangerous word here, decelerate. Decelerate, I say it's a dangerous word because it just can add confusion sometimes. For decelerate, that does mean we're slowing down. And it already established that our initial velocity was 10, which would be really a positive 10. So we're slowing down in the positive direction, which means our acceleration would have to be negative, otherwise we'd be speeding up. So I can write acceleration is negative 1.5 meters per second squared. Now jump to the question, how long? So we're looking for time. Will it take Jane to stop? She stops, which tells us the final velocity is 0. Once again, we're using that acceleration equation, but this time we're looking for time. So to get time by itself, right now it's underneath a fraction, which is a problem. I can't find time unless I get it up top first. So I'm going to multiply both sides by change in time. So these times will cancel, and we end up with time times acceleration equals change in velocity. Then to get time by itself, we'll divide by A. Those cancel. So all in all, time is change in velocity divided by acceleration. Or in this case, 0 minus 10 divided by negative 1.5. Which, if we were to plug that into a calculator, we get 6.6 repeating. I'm going to round to 2 decimal places because 2 decimal places is usually safe. So it'll be 6.67 seconds. Little over 6.5 seconds to stop. Then for part B, how far will she travel? How far will she have traveled in this time? So we're looking for how far, which is often displacement. Luckily, we've got an equation for that. Although I do want to make a note about this equation, something that we kind of gloss over sometimes during class when we're rushing for time. Our big ugly equation, I'll write it out in its entirety first. Now, technically, this equation does not have delta x in it yet. So we have 2 options. Option 1 is what I generally go with when we're going through class. And that's just to say, make the assumption that our initial velocity, or initial position, that our initial position is 0. Then I can just say that my final position will be my displacement. But rather than make that assumption, we could just subtract xi from both sides. If I did that, I would get xf minus xi on the left side is equal to all that other stuff. Then I just need to remember that xf minus xi is displacement. So I could simplify this, or rather substitute in and just say displacement is equal to all that other stuff. And luckily, we have all that other stuff. Initial velocity is 10. Our time we found in part A, 6.67. Our acceleration, negative 1.5. And our time, once again, 6.67. And we got to square it for the second one. Then carefully plug all that into a calculator, keeping in mind that your acceleration is negative. You should get 33.33. Rounding it to 2 decimal places, 33.33 meters. That's how far she'll travel before she reaches the stop, which is actually pretty far. Next up, 44. A race car crosses the starting line traveling at 40 meters per second. So at the start, it's already traveling that fast. It then accelerates. We've got the acceleration. We're looking for how far, and we've got the time. As a good rule of thumb, anytime you've got displacement or you're looking for displacement and acceleration is involved, there's accelerated motion happening, you're going to need the big ugly equation. And actually, I'm going to write it solved for displacement like we did on the previous problem, because that's what we're looking for here. Now for this one, I could make the assumption that our initial position is 0. We did just start a race, so that would make sense. But rather than make that assumption, it's just looking for how far in general. That's the displacement. I don't need to make that assumption. I can just solve for displacement right away by plugging in our givens into our equation. 40, our time of 5. Our acceleration is 9 here, and our time is 5 again. No algebra needed, just carefully plugging that into a calculator. $312.5. This is a displacement. Distances and displacements are measured in meters. That one was decently straightforward as long as you can recognize when you need to use that big ugly equation. Number 48. What is the average acceleration of a rocket that travels 400 meters in 5 seconds if it starts from rest? All right, let's collect our givens on this one. So we're looking for acceleration. We can go ahead and make that note that we don't know what the acceleration is, but we need it. We travel 400 meters, so I could say the displacement is 400 meters. Or I could also say that I'm launching a rocket. It's going to start from the ground, so my initial position would be 0, thus making my final position 400. You know the time is 5 seconds. And the other bit of information that's critical that we need is the fact that we're starting from rest, which means our initial velocity is 0. So then we look at our givens. I see that displacement is involved, and I'm looking for acceleration. So anytime we've got those two things, we're going to need our big ugly equation. There it is in all of its glory. We're going to be solving for A, meaning I need to get A by itself. So I could start moving stuff around to get an equation for acceleration, but actually on this one, I would recommend just plugging in your numbers first, because that's going to simplify the mess for us. So XF, we got 400. XI, initial position, is 0, so that just goes away. Initial velocity is also 0, meaning this whole term here, 0 times time, is going to be 0. So that whole thing goes away. So then I can go to the right. 1/2 A, I don't know what that is. I'll leave that as A, times 5 squared. Then to get A by itself, I might simplify that right side a little bit. 5 squared is 25, and then half of 25 would be 12.5. So we have 12.5 times A, and then just divide both sides by 12.5. Then toss that into a calculator. 32 meters per second squared. Once again, meters per second squared for acceleration. Jumping on over to the next one. We've got 52. I think this is the last one. Eve is standing at the top of a cliff. If she drops a rock off of the cliff and it takes 2.5 seconds to hit the ground, how tall is the cliff? This question I'm a big fan of because I like hiking, and this is a thing you can actually do to get a decent estimate on how high up you are. So here's our cliff. Here's Eve. And I'm going to actually say that she's dropping the rock. Say she's got a really long arm. She's dropping the rock from the very end of the cliff, which is what you'd want to do if you're trying to gauge how tall a cliff is. Drop right from the top of it. It's going to fall down, eventually hitting the ground on the bottom. And that's going to take us, well, it's going to take the rock 2.5 seconds to get there, which is the only number we have in the question. So if I go to list my givens, at a glance, kind of looks like we know time and nothing else. But there's actually a few other things we know. It said she drops the rock. That's a specific word. She didn't throw the rock down. She didn't throw the rock up. She just dropped it. She let go of it. That tells us that the initial velocity is 0. Likewise, we could say that her initial position, the rock's initial position rather, we could call that 0. And then our answer will just be its final position, which would give us our displacement. So I'm actually going to write XF unknown. That's kind of what I'm looking for here. There's something else we know. Eve is probably standing on Earth, and she's dropping something on Earth, which means we know the acceleration is going to be the acceleration due to gravity, which on Earth is 9.8 or negative 9.8 meters per second squared. But I'm actually going to make it positive on this one. So I need to make a note on my work here that down is positive. The reason I'm making it positive is just because I don't want to have to make a negative and deal with this negative there. But you could make a negative. That just would make your final answer negative, but we're just looking for the height, so the number is really all we need, or you could say the absolute value of the number is all we need. But anyway, making it positive, I see that I've got displacement, initial velocity, time, acceleration, all the things I need for the big ugly equation. And once again, we don't have to move anything around. We can just plug in and solve. Initial position, we said was 0. Initial velocity is also 0, so that goes away. Acceleration due to gravity in this case is 9.8. And the time is 2.5 seconds. So if you wanted to measure the height of a cliff or building or whatever, you're really just going to be doing 1/2 9.8 multiplied by however long it takes, squared. So if you have a phone handy while you're out and about hiking around, you can do that pretty quickly to get a decent estimate. So Eve here is standing on a cliff that is roughly 30.62 meters. Decently tall cliff. Now, the reason I kept saying roughly or approximately to that is this does ignore air resistance, which if you got a good smooth rock, then you kind of can ignore air resistance. For the most part, it will affect it a tiny, tiny bit, but not much. But if it's big flat rock, the air resistance might throw your calculation off a bit, but you'll still get a decent estimate, which really physics is all about getting decent estimates. We don't know anything exactly, but we can get pretty close. And that was the last one. So hopefully you've got your note card. If you have any questions, you can make a private comment on this post from Google Classroom, and I'll probably get back to you pretty quickly. Best of luck tomorrow.